The unified theory of electric machines, sometimes called the generalized or general theory. Although this is a relatively mathematical subject, I will try to explain the essentials without using excessively detailed mathematical equations, relying instead on some key diagrams and appealing to our physical imagination as engineers. I will include space vectors, and at the end I will briefly discuss the relationship between these concepts and the modern finite element method. It's a personal view. Although it is generously hosted by JSOL, it does not represent JSOL in any way. Here is an overview of the family of electric machines, the subject of the previous webinar. Engineering calculations can perhaps be divided into two categories: design and performance. These categories overlap to quite a large extent, but design calculations are essentially concerned with topology, dimensioning, the number of poles, the layout of windings, and the numbers of turns and the choice of materials. Performance calculations, on the other hand, are concerned with the behavior of the machine once it has been built, and they almost always include modeling of the supply and the control as well as the load. At the simplest level, performance calculations use inductances, generated voltages, resistances, and other circuit variables such as currents and flux linkages, and mechanical variables such as torque and speed. All these points apply to the entire family of electric machines which we see here, and in this talk we will be mainly concerned with the AC drive family, the ones colored blue. But let's start with the permanent magnet DC motor here at the top. These are the performance equations of the permanent magnet DC motor. They are very simple: EMF proportional to speed and torque proportional to current. The voltage around the circuit is in accordance with Kirchhoff's first law, and the constants Ke and Kt are both proportional to the flux phi or phi g, the air gap flux. These equations form the basis of the control not only of the permanent magnet DC motor but also of the wound field DC motor, which has the facility for adjusting the flux in order to modify the torque per ampere, the generated voltage, and the speed-torque characteristic. It would be very desirable for all of the control features of the wound field DC motor to apply to the AC machines, the blue ones, and especially the induction motor, which is nowadays the mainstay of variable speed drives in larger sizes, and equally to the permanent magnet brushless AC motors in smaller sizes. But they don't. The equations of all the AC machines are more complicated because at first sight nothing is constant. The flux rotates while the currents and voltages follow more or less sinusoidal waveforms in time. Also, in the AC machines we have to control 3 currents instead of 1, and in the case of the wound field synchronous motor, the field current as well. The need for performance calculations has been clear from the beginnings of electrical engineering. Here is the scheme of the AC power transmission system installed at the International Electrotechnical Exhibition in Frankfurt, Germany in 1891. We can see generators, a mixture of loads including lighting and induction machines, cables, transformers, fuses, meters, and switchgear, all in a 3-phase circuit running at up to 30,000 volts and stretching over 175 kilometers from the hydroelectric generating station at Laufen am Neckar, a tributary of the river Rhine. Here we see the schematic circuit of a wound field synchronous motor fed from an inverter, which of course includes power electronic semiconductor switching devices, and here on the rotor a diode rectifier feeding the field winding. However, if we observe an AC motor in operation, we don't get the impression of wild variation of current or voltage or speed or torque. It doesn't look complicated, and inside it appears to be simpler than a DC motor. In the steady state, everything looks settled and unvarying. So here is the germ of the idea of a mathematical transformation or mapping in which we start with the actual voltages and currents at the terminals, and in effect, by a transformation process, substitute these variables by a set of variables which are somehow locked to the rotating flux and therefore remain constant, at least in the steady state. That is exactly what we can see in a field-oriented control diagram like this one with ISD and ISQ. Now, whereas the circuit diagrams in the previous two slides represent currents and voltages within the actual circuits, this diagram defines the relationships between signals representing the values mainly of currents but also of speed and torque. It is this type of signal diagram that is used to define the architecture of the microelectronic controller, and in some sense it captures the entire performance of the complete system. This example is for the field-oriented control of an induction motor. It's one of the earliest schemes attributed to Felix Blaschke and Siemens in the late 1970s, and marvelously described in the books by the late Professor Leonhard. Let's look closely. Here we see three currents IA, IB, IC, real numbers whose values are the actual instantaneous amperes flowing into the respective motor windings. They are measured by current transducers located in the output leads of the inverter and therefore in series with the motor windings. The box with the label 3 to 2 describes a processing function which is executed digitally in the microelectronic controller. What it does is to transform the three line currents into two currents, ISD and ISQ, still real numbers, still instantaneous values. This is known as a three-phase to two-axis transformation, and it's similar in concept to Parkes transformation, which we will see later. In field-oriented control theory, ISD and ISQ are the real and imaginary components of a complex number which is called a space vector, and in the steady state they are constant. Let's leave this diagram for a short time to take a closer look at the definition of the space vector. We'll come back. Here on the left we see a DC motor cross-section in which the main flux phi is established by field poles in the vertical direction. We can also see the armature current I, which flows through the rotor and establishes its own magnetic flux. The direction of this flux, the armature reaction flux, is more or less orthogonal to the field flux. The pattern of ampere conductors which establishes the armature reaction flux has a fixed shape or spatial distribution. But once that distribution is given, we can focus on just two parameters that define its main effects: the magnitude I in amperes and the direction, which is determined by the angular position of the brushes. Even though the armature conductors are rotating, the direction or orientation of the pattern of ampere conductors is actually fixed in space by the action of the commutator and brushes. By rotating the brushes, we can alter the orientation of the armature current and thus control its effects. Even in the DC motor, it helps to resolve the current vector, if you will, into two components, one of which is aligned with the field poles and modifies the overall flux and therefore also the terminal voltage, and the other one which is orthogonal to the field axis and controls the torque. Here we have the essence of field-oriented control, that is, the independent control of flux and torque. And it involves the resolution of a current vector into components which have a certain spatial orientation, especially in relation to the main field axis. The main field axis is distinct in some machines, but not in others. But in all cases it is denoted as the d-axis or the direct axis. Mathematically, the process of resolving the current, or more precisely the ampere conductor distribution, into d and q axis components is actually a reference frame transformation or mapping. Now let us consider the stator winding of an AC machine in which a sinusoidal spatial distribution of ampere conductors sets up a sinusoidally distributed flux phi. The important property of this flux distribution is its fundamental space harmonic component, which has two key parameters, the magnitude phi and the direction. In the normal AC machine, the flux phi is rotating at synchronous speed, and the ampere conductor distribution includes all three phases. In comparing this with the field system of the DC machine, there are three obvious differences. First, in the DC machine the flux phi is stationary, but in the AC machine it rotates at synchronous speed. However, if we imagine ourselves to be an observer on the rotor, the flux will appear to be stationary, and so we can dismiss this difference as a mere detail. Secondly, the field poles on the rotor of a synchronous machine are usually on the inside, whereas in the DC motor the field poles are on the outside. But for the purposes of our argument, we can dismiss that too as an unimportant detail of topology, because what is important is the relative motion between the rotor and the stator, not which one is stationary and which one is rotating. Thirdly, the flux in a DC machine has a more or less rectangular distribution, spatial distribution around the armature, whereas in the AC machine we're concerned with the fundamental space harmonic component, which of course is sinusoidally distributed. The shapes of these distributions are of course vital in the design and operation of the respective machines, but for our purposes they do nothing more than to give rise to coefficients which appear in the performance equations and then are seen no more. Now, if we have a sinusoidal distribution of ampere conductors, we can, in precisely the same way as in the DC motor, characterize its effectiveness by the same two parameters, the magnitude I in amperes, give or take a coefficient which we've just mentioned, and the direction. Such a distribution represents the fundamental behavior of the windings of an AC machine, and the two parameters, I and the direction, are components of what we call a space vector. We will see that there is a space vector for each phase winding, and another space vector that combines the effects of all three phases. In the induction motor we will find a similar set of space vectors for the rotor as well. In a typical AC machine with three phase windings, we have a space vector for phase A, one for phase B, and one for phase C. Each one of these is stationary in space, but its amplitude is proportional to the instantaneous current in the respective phase winding. Now we can define the spatial directions in the so-called Argand diagram, complex plane, by means of three complex numbers, one along the real axis, A at 120 degrees and A squared at 240 degrees. Multiplying any complex number by A represents nothing more than a rotation of 120 degrees. The complex numbers 1, A, and A squared all have magnitude 1, and they define a three-phase frame of reference for the three-phase windings and their effects along their respective phase winding axes. That's because the phase winding axes are normally displaced 120 degrees from one another in physical space around the bore of the stator. When we say 120 degrees, of course we mean electrical degrees. So 120 degrees means 2/3 of a pole pitch being 180 electrical degrees, and two pole pitches 360 electrical degrees. We can also say that the complex numbers 1, A, and A squared are themselves space vectors, or unit space vectors along the three winding axes. Now, if we simply add the three complex numbers representing the space vectors of the individual phase currents, the result is itself a space vector, another complex number Is, but the orientation of this one is not fixed. It depends, obviously, on the values of the three phase currents, as does its magnitude. When the three-phase currents follow a sinusoidal pattern, as they do in steady-state operation, it turns out that Is is fixed in magnitude and rotates steadily at synchronous speed. Now here we have the very essence of the operation of the AC machine, at least in terms of one of its variables, the current, or more precisely the fundamental space harmonic of the ampere conductor distribution, current for short. But the space vector concept applies equally to the voltage, being defined from the three-phase voltages, instantaneous voltages, in exactly the same way that the space vector of current is related to the three-phase currents. Likewise, there is a space vector of flux linkage, which is analogous to the flux phi in the DC machine. I should mention that there is a convention in which a scale factor of 2/3 is applied to the sum of the three phase space vectors, in order to keep the peak value of the resulting space vector equal to the peak value of the phase current in the steady state. Now, it should be easy to see that although this diagram is drawn in the ordinary complex plane, with the real axis along the x-axis and the imaginary axis along the y-axis, the space vector Is can be further resolved along two orthogonal axes d and q. In this dq frame of reference, the components are ISD and ISQ, and they are written as real numbers. We could write them in boldface as complex numbers, space vectors, but there's no need to do that because their orientation is implicit in that of the dq frame of reference, which carries them. Now we come to two important principles. First, we can observe that the orientation of the dq frame of reference is arbitrary. For example, in an induction motor, we can orient it in such a way that the d-axis is aligned with what is called the rotor flux, or more precisely, the space vector of the flux linkage of the rotor circuits. This is what is done in Leonhard's field orientation diagram. The orientation of the dq frame of reference is not the only one. But the only point I would like to make here is that different orientations lead to different architectures for the microelectronic controller, and this has proven to be important in the development of field-oriented control systems. The second principle is that when we have two sets of windings, stator and rotor, one of which is rotating relative to the other, we have two sets of space vectors defined in their respective frames of reference. And of course, the flux linkages between the two sets of windings are mutually coupled. We therefore expect the electromagnetic induction of voltage in each set of windings when the current is changing in the other set or when there is relative rotation. In this case, the transformation of a space vector from one frame of reference to the other involves nothing more than a rotation operator, which we see here as e to the j beta between the primed set, the rotor frame, and the unprimed set, the stator frame. Beta is the angle between the two reference frames, and the transformation by e to the j beta, or e to the minus j beta going the other way, is known as a projection or a rotation transformation. When we substitute this transformation into the voltage equation, we find two kinds of induced EMF emerging from the chain rule of differentiation with respect to time. P, boldface P, is d by dt. So one of these terms, the P term, is the so-called transformer EMF, and the other one, the j omega term, is the so-called speed EMF or rotation EMF. The speed EMF arises from the differentiation of the transformation function e to the j beta itself. And when we analyze the power balance, we find that the speed EMF works with the current to produce the torque. All of this is, of course, well known in classical theory, but without laboring the details, we can see that these results emerge with extraordinary economy and elegance in terms of the space vectors. At this point, we can note how the space vector can be used to model the inverter. Here is an inverter circuit in which the transistors are modeled by single pole switches, which are either open or closed, on or off. And normally in an AC sine wave inverter, 3 transistors are on and 3 are off. And the particular combination defines the voltages at the 3 terminals of the motor. There are 2 additional states where all the uppers are on and all the lowers are off, and vice versa, making a total of 8 valid states. Each of these states defines a voltage space vector at the motor terminals. Thus we can say that the space vector unites the theory of the motor with that of the inverter, not only at the power electronic switching frequency, usually a few kilohertz, but also at the lower frequencies of voltage and current variations on a timescale meaningful to the motor. At this point, I would like to break off to show Park's transform. The conventional diagram shows the 3 phase windings A, B, C, with their axes displaced 120 electrical degrees around the stator periphery. And then we see the field winding of a synchronous machine which defines 2 orthogonal axes, D and Q. Clearly D is the axis of the field poles, the direct axis, and Q is the so-called interpolar or quadrature axis. The DQ axes are rotating while the ABC axes are stationary. In the space vector diagram, we started with a reference frame for the stator and one for the rotor, and transformed everything into one reference frame by means of the transformation e to the j beta, which we called a projection. In this diagram also there are 2 frames of reference, DQ and ABC. What Park's transformation does is to map the stator currents, voltages and flux linkages in the stationary ABC frame of reference into the rotating DQ frame of reference, so that all variables will be in the same frame of reference, which in the case of Parkes transformation is locked to the rotor and rotates at the speed of the rotor. There are other three-phase to two-phase to two-axis transformations in which the DQ axes rotate at different speeds or don't rotate at all, and these transformations are useful for various purposes, but we don't need to give them any further consideration here. Let us express the ABC currents by a vector, not a space vector, not a complex number, but simply an array of three numbers, or a column matrix with three rows, and the DQ currents by another column matrix. Then the transformation takes the form of a matrix multiplication. We do the same for voltages and flux linkages, and the result is a set of currents, voltages, and flux linkages in the DQ frame, which are rather like the ones in the space vector diagram. And indeed they are practically the same. In the steady state, the currents ID and IQ are constant in Parkes DQ frame, while the space vector components ISD and ISQ are constant in the DQ reference frame that we defined to be rotating in the complex plane. Only the orientations of the two DQ frames are different. In Parkes transformation, the DQ frame is locked to the rotor, but the space vector DQ frame can have any orientation we please, including, in the case of the synchronous machine, the same orientation as Parkes DQ frame. In the ABC frame of reference, the voltage equations are these at the top. They can, of course, be solved as they stand, and sometimes they are, but we have to have a relationship between currents and flux linkages in order to complete the solution. And this relationship is very complicated because the necessary inductances vary widely and rapidly with all three currents and also with the rotor position. The result of Parkes transformation is that the number of inductances is greatly reduced from 9 to 2, even without counting the field winding in the synchronous wound field machine. We can see this in the next slide. The current flux linkage relationship is often expressed by inductance, and here on the left we have some simplified expressions for the self-inductances of the phases and the mutual inductances between them. Theta is the rotor position, and we can see very large variations. The inductances are nothing like constant. The graph on the right shows some of these inductances measured on a synchronous machine in 1906, so the problem has been known for a long time. These graphs show a higher harmonic content than the simple trigonometric expressions on the left, but in general it's too complicated to include higher order harmonics, and they are generally ignored. Even this is far from the complete story, because all the inductances vary with phase currents as well as rotor position. In spite of all these limitations, in mathematical language, Parkes transform diagonalizes the inductance matrix so that we end up with three inductances, LD, LQ, and LZ, which are nearly independent of each other. In fact, the third one, the zero sequence inductance, is of no consequence when we're dealing with a three-wire connection, which is the normal case. So we're left with only two, the synchronous inductance in the direct axis, LD, and the synchronous inductance in the Q axis, LQ. And these are the inductance equations or flux linkage equations in the two axes for a permanent magnet motor where psi m is the flux linkage produced by the permanent magnet. Now, we arrived here by a process which produces constant values of LD and LQ, but we also anticipated the effect of saturation, and it turns out that we can compute LD and LQ by a very efficient finite element process in which the rotor remains stationary in one position. This is an example for an IPM, interior permanent magnet motor, except that we're plotting flux linkage versus current instead of inductance in each axis. The inductances can be assumed to be the slopes of these curves. So the d-axis curve begins at zero current with the d-axis flux linkage due to the magnet, psi m, and as we apply current in the positive direction, the flux linkage increases. The slope of this curve is practically constant and not very large, indicating that LD in this particular IPM is quite low and not greatly affected by saturation. In the Q-axis, the flux linkage current curve starts with a large slope, the unsaturated Q-axis synchronous inductance LQ. But as the Q-axis component of current increases, it flattens out rather quickly, showing that the Q-axis magnetic flux path saturates quickly, much more so than in the D-axis. I'm grateful to my colleague Yves Jolière at PowerSys for computing these curves for the IPM example in one of the PowerSys training courses. Now, without writing out the equations, even though they are quite simple, we should take note here of the importance of these curves. Once we know the flux linkages and the current in the DQ axes, we can immediately calculate the torque and the terminal voltage. An estimate of the torque is obviously needed in the field-oriented control scheme. If we have a PWM current-regulated inverter, we will be controlling the current. In fact, we will have a closed-loop control generates a current demand signal, just as we saw in the induction motor controller earlier. But we also need to know that the inverter has enough voltage available to drive this current. So that is why the voltage calculation is important. Here is a conceptual reproduction of the curves in the previous slide, but modified to show the effect of cross-saturation. That is, the D component of current affects the Q-axis flux linkage and vice versa. This happens in practical motors, but the extent to which it happens depends on the particular motor design. We can say that in general, the complete map of these values is needed only in cases where very high accuracy is required. And of course, the effect of cross-saturation can be calculated using the same finite element procedure that we used in the previous slide. That is one in which the rotor position remains fixed. Finally, I must draw this to a close. In a short session like this, we cannot possibly demonstrate the software implementation of these principles, but only show a pointer. Detailed descriptions of these methods are presented in the PowerSys training seminars, which are beyond my scope here. But the thing to bear in mind is the efficient linkage between circuit simulation on the one hand and finite element calculations or field calculations on the other. There are, of course, second-order effects which I have not covered here. For example, the effect of spatial harmonics on the variation of LD and LQ, and in the induction motor, the whole question of determining the rotor currents which are driven by electromagnetic induction and not by a current-controlled PWM inverter. Real windings are not sinusoidally distributed. In fact, it is impossible to make a truly sinusoidal winding distribution. For that reason, we must use Fourier series to perform a harmonic analysis of the actual winding and extract the fundamental space harmonic for purposes of the performance calculations. What happens to all the other harmonics? Well, they produce parasitic effects, torque ripple, additional losses, and they appear as additional leakage inductance, harmonic leakage inductance, but all these effects are usually of secondary importance and do not change the fundamental control behavior of the machine. Oh yes, and I haven't even mentioned eddy currents or core losses. But all these effects are of course within the scope of the most advanced software tools, and in thinking about that I can't escape the conclusion that what I've been describing is actually the elementary theory of the AC machine. But this diagram suggests an interesting idea, a redefinition of what used to be known as the universal theory of electric machines. Given the right software tools in circuit simulation and field calculation, and an efficient linkage between them, that is, in effect, exactly what we have, a universal theory of electric machines. The old unified theory was developed to unify the circuit theory of DC and AC machines, but the new unified theory is a software system that unifies the field theory with the circuit theory, a very powerful idea. By incorporating the space vector, it even links itself to the control of inverters, which of course was completely absent in the original unified theory. Thanks for listening.